Okay. Question number 4. Express 1 by 3 plus 3i whole cube in the form of a plus ib. So z1 plus z2, we can use the formula a plus b whole cube. Using a plus b whole cube equal to a cube plus 3a square b plus 3ab square plus b cube. By using this you can write 1 by 3 plus 3i whole cube equal to 1 by 3 whole cube plus 3 into 1 by 3 whole square into 3i plus 3 into 1 by 3 into 3i whole square plus 3i whole cube. That is equals to 1 by 27 plus 3 into 1 by 9 into 3i plus 9i square plus 27i cube. So it is equal to 1 by 27, 3 3 is a 9 plus I minus 9 plus 27 I square into y. So it is 1 by 27 plus I minus 9 minus 27i. So in this case it is 1 by 27 minus 9 minus 26i. So your LCM is 27. 1 minus 9 7 is 63, 6. Carry 9 to the 18, 18 6 24 minus 26i. So you can write minus 242 by 27 minus 26i. Now this is in the form of a plus ib. Now next one. Question number 5. Express minus 2 minus 1 by 3i whole cube in the form a plus ib. So using a minus b whole cube or a plus b whole cube equal to a cube plus b cube, a cube plus 3a square b plus 3ab square plus b cube. So you can write minus 2 minus 1 by 3i whole cube equals to minus 2 plus 1 by 3i whole cube. So let this is 1. Now 2 plus 1 by 3i whole cube. By using this formula, when we use this formula we can write 2 cube plus 3 into 2 square into 1 by 3i plus 3 into 2 into 1 by 3i whole square plus I by 3 whole cube. So you can write this is equal to 8 plus 3 into 4 by 3 I plus 3 into 2 I square by 9 plus plus 1 by 27 I square into I. So you can write this is 8, 3 is 9, 8 minus 2 by 3, and here this 3 and this 3 will be cancelled. This will be 4I minus 1 by 27I. So it is 24 minus 2 by 3 plus 4 minus 1 by 27 into I, that is 22 by 3 plus 108 minus 1 by 27I. So you can write 22 by 3 plus 107 by 27I. This is 2. This is the cube of 2 plus 1 by 3 I whole to the power 3. Now using 2 in 1. By using 2 in 1, we get minus 2 minus 1 by 3I whole cube equal to minus 22 by 3 plus 107 by 27I, open the bracket, that is minus 107 by 27I. So this is in the form of A plus IB. Now find the multiplicative inverse of the following. Next question. Question number 6. Question 6. Find the multiplicative inverse of the following complex number. Number 1, 4 minus 3I. Number 2, root 5 plus 3I. And 3, I or minus I. So you write the solution. Given that z equal to 4 minus 3I, its conjugate z bar equal to 4 plus 3I. It is obtained by changing the sign of imaginary terms. Imaginary terms is minus 3I, change that plus 3I. So it becomes conjugate of z. Now modulus of z is under root 4 square plus minus 3 square, that is equal to 5. So mod z square is 25. So multiplicative inverse 1 by z equal to z bar upon mod z whole square. So it is 4 plus 3I upon 25. So that is equal to 4 upon 25 plus 3 upon 25I. So in this way we find the multiplicative inverse of other numbers. Now express the following in the form of A plus IB. Question 7. Express the following in the form of a plus ib. So 3 plus under root 5 multiply by 3 minus under root 5 upon root 3 plus root 2i minus root 3 minus root 2i, that is, you solve them. A plus b, a minus b. This is in the form of a plus b into a minus b. It is a square minus b square. So 3 square minus root 5i whole square. This is equal to a square minus b square. In the denominator, open the bracket, root 3 plus root 2i minus root 3 plus root 2i. So this root 3 and this root 3 will be cancelled, and this is 9 minus 5i square upon root 2i plus root 2i is 2 root 2i. So you can write 9 plus 5 upon 2 root 2i. So that is equal to 14 upon 2 root 2i. So you can write 14 root 2 upon 4i. 2 to the 4, 2 7 the 14. That is 7 root 2 upon 2i. Multiply by I, divide by I. You will get 7 under root 2i upon 2i square. I square is minus 1. So it is minus 7 root 2 by 2 I. So you can write this is equal to 0 minus 7 root 2 by 2 I. This is in the form of a plus ib, where a is 0 and b is minus 7 root 2 by 2. Argand plane and polar representation. Polar representation. So, as you know that ordered pair of real numbers can be represented in xy plane with reference to two mutually perpendicular lines, that is known as x axis and y axis. For an ordered pair xy of real numbers, we get a unique point in xy plane, that is also known as Cartesian plane. With reference to two mutually perpendicular lines as x-axis and y-axis. So now you see, this is the Cartesian plane, this is x-axis and this is y-axis. 1, 2, 3, 4, 5, and here -1, -2, -3. This is 1, 2, 3, 4. This is -1, -2, -3. This point is 2, 4. 2, 4 is an ordered pair of real numbers, and corresponding to this ordered pair, that can be represented in xy plane, and for every point there is a complex number, and for every complex number there is a point in this plane. Both the conditions are satisfied, and similarly any point on the x-axis is of the form 2, 0, its y coordinate is 0. So in ordered pair, y is 0, x is there, and now this point is on y-axis. For this, this point is known as 0, 1. So similarly, here in this quadrant, your point is -1, 4, and in this quadrant, your point is -2, -2, and in this quadrant, your point is 4, -2. And you mark them, your point, this as A, and this as B, this as C, this as D, and this is E, and this is F. Corresponding to the point A, B, C, D, E, F, there are complex number 2 plus 4i. Your A can be represented as this ordered pair xy can be 2, 4, can be represented as 2 plus 4i. So this horizontal axis, x-axis is known as the real axis, and y-axis is known as the imaginary axis. And similarly, your point B can be written as -1, 4, and it is -1 plus 4i. And now you come to third quadrant, your point C, -2, -2 can be written as -2, -2i. And a number on an ordered pair on x-axis, that is 2, 0, is of the form 2 plus 0i, and an ordered pair on y-axis is of the form, that point is 0, 1, that is 0 plus I. Now come to the result. After showing all this kind of things, what you get the result? How can you define the organ planar complex plane? Now need to define organ plane or complex plane. How can you define? Complex plane or organ plane is a plane in which for every point we get a complex number. A plane having point and corresponding to each point, we have a complex number. Known as complex plane or organ plane. Or organ plane. Once again, I am repeating this thing. Complex plane is a plane having point, and corresponding to each point we have a complex number known as the complex plane or Argand plane. For example, for a point xy, which is in the form of ordered pair, for a point xy we have a complex number z equal to x plus iy and vice versa. So what we can conclude for that? For every complex number in the plane, in xy plane, in Cartesian plane, there is a point xy, and for every point xy, there is a complex number x plus iy, which I have shown you by making coordinate plane, and I have shown the point and the corresponding complex number in that plane. Now, for the complex number z equal to x plus iy, some illustration you can see here about the complex number. Suppose this is a xy plane, xo x dash, yo y dash, this is xy plane, and there is a point pxy. This is also a complex number z, and you join O and this point P, length of OP is R, so you can write your complex number z equal to x plus iy mod z, modulus of the complex number z is under root x square plus y square, and this under root x square plus y square is the distance, this is the distance of the point, pxy from origin. And as you have taken OP is R, so you can write your R is length of OP, R is mod z, that is equals to under root x square plus y square. You have seen the formula distance between 2 points x and y and origin in your previous classes. So distance between x, y and origin is under root x square plus y square. Now you can say that your this axis is real axis, any point, any complex number on x axis is of the form a plus 0i, and any complex number on y axis is of the form 0 plus bi, and x axis is known as real axis, and similarly y axis is known as imaginary axis, Now, next thing is that here if you take the mirror image of the point pxy in x-axis, then what happens? Your point qx minus y is the mirror image of xy in x-axis, and you can see here. So you can write qx minus y is the mirror image of pxy. Here in this figure, qx minus y is the mirror image of pxy in x-axis. This is mirror image in x-axis. Now polar representation of complex number. Next topic is polar representation of complex number. Polar representation of complex number. This is your Cartesian plane, xy plane, x dash, y, o, y dash. Let a complex number z equal to x plus iy is taken in xy plane. This is the point P, Z. It is z equal to x plus iy. Let a directed line segment OP is of length R and OP makes an angle theta with the positive direction of x-axis. So an ordered pair P, you join this OP, this is R and this angle is theta, positive direction of x-axis. So an ordered pair P R theta, this becomes polar coordinate P R theta. An ordered pair P R theta of real numbers is called the polar coordinate of P. And theta origin is as the pole, and origin is as the pole, and x-axis as initial line. This is the initial line. So now this is the information I have understood. This thing here in this complex plane, in xy plane is complex plane. This is also organoid plane. So z equal to x plus y is taken in xy plane. Let a directed line segment OP is of length R and OP makes an angle theta with the positive direction of x-axis. An ordered pair P R theta of real numbers is called the polar coordinate of P, and origin is as the pole and x-axis as the initial line. So now you observe this in this figure. Come to this. In this figure, when you draw a perpendicular from P on x-axis, then what happens? Now you get two lengths. One is along the x-axis and another is parallel to x-axis. There is two length. Draw PM perpendicular to x-axis. Then what happens? This is M. So your one distance x is written as OM and y is written as PM. So in right angle triangle, in right angled triangle OPM, we can write cos theta is equal to OM by OP. Cos theta is equal to OM is x, OP is r. So x can be written as r cos theta. Similarly, by taking sin theta, you can write y equal to r sin theta, and you can write your complex number z. Complex number z can be written as, you can write z as x plus iy, substituting x and y here in terms of r and theta. You can write r cos theta plus ir sin theta, and z equal to x plus iy can be written as r in the bracket cos theta plus I sin theta, which is known as the polar form of the given complex number, which is known as the polar form of a given complex number. Complex number z equal to x plus iy. Z equal to x plus iy. So now for any complex number, now come to another point. Your r is, you have seen earlier, I have shown you, your r is mod z and theta is known as argument of complex number z, and this tan of theta is equal to y upon x, that is imaginary part of z upon real part of z. So from this information you can obtain theta, and from the property of modulus of a complex number you can find r. After finding r and theta, when you substitute in 1, you will get the polar form of the complex number. Now you see, now I am talking about how can you find the argument of a given complex number z. So in this case, for a given complex number z equal to x plus iy, you find r equals to mod z and tan theta equals to y upon x. From this relation you find theta and r and you substitute in 1. So how can you obtain your theta? So as you know, there are 4 quadrant system. This is your first. Your theta is measured in anti-clockwise direction because your angle theta is positive. This is your first form of the complex number represented by the point P, and now this is the second. In second quadrant, if your complex number lies in second quadrant, then again your theta is this is second, and now if your complex number is in third quadrant, then your angle this theta is measured like this is your third form, and if your complex number is in fourth quadrant, so like that, so your angle measured is this. So this is the range 0 is less than or equal to theta is less than 2 pi. So we are not, this is not the range of principal value of theta. So we are talking here, we take that theta which lies in the principal value. So what is the principal value? We will take another interval. Suppose this is an interval 0 to 2 pi. So we will take another interval that divides your complex plane, xy plane, in two equal parts. For example, your x-axis divide this xy plane in two equal parts. This first part is taken from 0 to pi. And second part, this will be taken from minus pi to 0. So in this way you can see, so we consider an interval whose length is similar to this interval, but it divides the whole complex plane, whole xy plane into two equal halves. So how can we take the interval? Minus pi is less than theta is less than or equal to pi. The length of this interval is also 2 pi, and this x-axis divides the xy plane in two equal halves. So your principal solution, principal value of theta lies in this interval. So how can we define that? You see, if your complex number lies in first quadrant, like this is the complex number, this is theta. This is first case. Your complex number lies in second quadrant. This is your P, this is theta. You show your theta like this, and when your complex number lies in third quadrant, so your angle is measured in this way for this interval, and this is your third case, and your fourth case, when your complex number lies in fourth quadrant, your angle is this. This is fourth, and this is the representation for the interval minus pi is less than theta is less than equal to pi. So its length is also 2 pi, and length of this 2 pi, length of this interval is also 2 pi. So we can say that this is not the principal solution. This is the solution from 0 to 2 pi. And when theta lies in these intervals, so in that case we get the principal solution of the equation tan theta equal to y by x, and that theta we will consider for the polar representation of a complex number. So now come to question. Represent the complex number question. Represent the complex number z equals to 1 plus I root 3 in polar form. So you have seen your polar form of the complex number is taken as that is equal to r cos theta plus I sin theta. This is the polar form. This is the polar form. Now you decide in which quadrant, before doing anything. First of all, you decide in which quadrant your given complex number lies, because on the basis of that we are taking the principal solution for theta. So your 1 plus I root 3, here x and y both are positive. So when x and y component of ordered pair x, y are positive, then that point lies in the first quadrant. So this complex number lies in first quadrant. 1 plus I root 3, in ordered pair you can write 1 root 3, and this lies in first quadrant. So now, as you know, R equals to modulus of z. So modulus of z can be obtained as 1 square plus root 3 square, that is equal to under root 1 plus 3 under root 4. So your R is 2 unit. Now tan theta is equal to y upon x, your imaginary part. Imaginary part of complex number is root 3 and your real part is 1. So your tan theta is root 3. As theta lies in your first quadrant, when your complex number p lies in first quadrant, then what happens? What is the value of theta? Your theta is this, that is measured from the positive direction of x-axis, and in this way value of root 3 is the value of tan 60. Tan 60 is tan pi by 3. So you can write tan theta is equals to tan pi by 3. So this implies that theta equals to pi by 3. So your R is 2, theta is pi by 3. Substitute in 1. This is 1. Substitute in 1. You get the polar form of complex number. So our polar form equals to 2 in the bracket cos pi by 3 plus I sin pi by 3. That is the polar form. That's all for today. Thank you.